Hello friends and welcome to Notebook. On certain roads near our house, you must have seen the warning, Accident Prone Zone. When we see such a warning, we immediately become cautious. We drive slow and take necessary measures. Thus, the warning helps us to avoid an accident. So, how do we know that particular bend is an accident-prone zone? Is there always an accident that occurs there? If there are no accidents, then what is the use of having a warning there? To answer the first question, the concerned authorities for road safety must have collected facts and figures that many accidents have occurred in that road. And most of the accidents on that particular road have occurred at that certain point. The facts must have been collected by someone through a certain period of time on certain duration each day and using certain measure. Don't you think so? After analyzing the facts, they must have come to the conclusion of that particular warning. Now, to answer the second question, we will see that there are no accidents every time a car passes that point. But basing on the facts and figures collected, there might be accidents. That is, the chances are high that there is an accident right at that point in the road. Now, coming to the third question. Since the warning is there, we get cautious and are better prepared to avoid an accident. Thus, all of the above answers are basically based on the facts and figures collected initially. These facts and figures are nothing but data. Confusing? Well, that is the reason a great man had once said, there are three kinds of lies: lies, damn lies, and statistics. Do you know who said that? The world, in fact, the universe around us, is composed of billions and trillions of facts and figures or data. If we know how to sort out data so that it may help us to arrive into warnings, good or bad, don't you think it will help us to lead a more informed life? This sorting of data is called statistics. And even though such warnings may never occur, but they make us better prepared to face a situation. Like in the above example, we get cautious about the accident. In fact, since we become cautious, for us, the accident is almost never there. Thus, we may think that the warning is a lie. There, do you see the trick of statistics and numbers? It has made you accept a notion irrespective of whether it will happen or not. In this lesson, we learn about how data is collected, how they can be sorted, and how they can be represented. Let us quickly look at some meanings and definitions. Data are all the facts and figures which are collected together for reference or analysis. Statistics. It is the practice or science of collecting, analyzing, interpreting, and presenting large quantities of data for the purpose of drawing inferences from a representative sample. Primary data. Data collected primarily for the purpose of a given inquiry are called primary data. Secondary data. When data is obtained from another source which already had the information stored for any other purpose, the data is called secondary data. Once we have collected data, we need to sort, present, and analyze them with various logical and mathematical tools. Statistically speaking, it is unlikely that you will need to explain in your exam the various terms by definition or meaning. It is more likely that you will apply those tools in practical problems. Thus, we will look at an illustration to learn about them. A data is obtained pertaining to number of plants in the garden of 100 houses in a locality. At first, data will look like just a bunch of numbers that are not classified or sorted. This data is ungrouped data or raw data. If we carefully scrutinize the data, we will find that the lowest and the highest number are 23 and 98 respectively. it will be easier if we can arrange them in ascending order. Thus, we can say that range of the data is highest value to lowest value. Range equals to x100 minus x1, where x is the variable that can take any numerical value. In our present problem, it is the number of plants. Thus, x100 is the number of plants in the 100th house, and x1 is the same for the first house when they are arranged in ascending order. Thus here, range is equal to 98 minus 23 is equal to 75. We see that when the data is so large, it is very time consuming and difficult to scrutinize and then put the same in ascending order. Thus, we sort and condense the data into groups to make it easier. Now, since the data lies between 23 to 98, in order to make it coherent, we create small groups or bins like 20 to 29, 30 to 39, etc. They are called class intervals. If you see the second column, there are lines and scratches which are called tally marks. If we see the first row, which is the first class interval, each scratch represents those houses where the number of plants are 20 or more and 29 or less. In the data, there are 3 such houses. That is, the houses with 23, 27, 28 plants. Thus here, x takes the value between 20 to 29 3 times. Similarly, if you see the class interval of 70 to 79, there are 10 times when x is any value between 70 to 79. Thus we put 10 scratches. Even in our scratches, we group them to make it easier. 2 groups, each of 5 scratches. 4 vertical and 1 diagonal striked through the first 4 to mark the completion of one group. If you see the third column, it is basically a numerical representation of the second column. This is called the frequency of the data. For our convenience, we will call frequency as f. Note, for each class interval, the smaller number is called lower limit and the upper number is called upper limit. Notice that for each interval, the upper class limit of one interval and the lower class limit of the next interval are different. This is not a problem when the data is basically the count of some phenomena, like the number of plants here. But if the data describes something like height, weight, length, etc., the variable x can be a fraction. Then we have a problem, as it doesn't specify where should we put such a data. For example, if in the above case, we were to find the length of the plants in inches and one of the values was 49.5, we couldn't be sure where to put the data in the 2 consecutive interval 40 to 49 or 50 to 59. In this case, for any class interval, we do the following. Upper limit of the next class minus lower limit of the concerned class whole divided by 2. Then we subtract and add the subsequent result from the lower limit of the next class and upper limit of the concerned class respectively. Thus now the class limits are 49.5. Generally, we have class intervals of equal width or size. That is, for every class, upper limit minus lower limit are equal. In that case, we can construct a table with continuous class intervals by subtracting 0.5 from the lower limit and adding 0.5 to the upper limit of a class. This kind of representation of data into groups or bins is called grouped data. This is used mainly for large number of data. Up till now, I hope you've got some basic understanding clear about data and how to represent them. In most times when we have data, it's difficult to construct a distribution and analyze the data in our mind. To quickly and effectively understand the data, we often use pictures and graphs. As is said, one picture is better than 1,000 words. Let us see some of the ways by which we do it. Bar graph. A bar chart or bar graph is a chart that presents categorical data with rectangular bars with heights or lengths proportional to the values that they represent. The bars can be plotted vertically or horizontally. A vertical bar chart is sometimes called a column chart. Consider our previous example of number of plants in gardens in the table. We take the class intervals in the x-axis and frequency in the y-axis. Plotting the information and drawing rectangles, we get a column chart. If we had plotted the intervals on y-axis and the frequency on x-axis, we would have gotten a bar chart. Remember our continuous distribution table? For such data, we generally construct a histogram. A histogram is a graphical display of data using bars of different heights. In a histogram, each bar groups numbers into ranges. Taller bars show that more data falls in that range. A histogram displays the shape and spread of continuous sample data. Let us consider our example of length of plants for continuous class intervals. If you see carefully, the length of bars are basically the frequencies. Thus, we can say that the areas of the rectangles are proportional to the frequencies, as area is the product of length and breadth. Here the breadth or class intervals are equal. What if the breadth is not equal? Won't we get a wrong representation in that case? Yes, we will. We will do a small trick of unitary method to solve that. Consider the same example with a twist. We have grouped the last two class intervals into one. When a histogram is constructed, it will give a wrong result. So to address this, we take the smallest class width or size in this table, that is 10. The last interval class size is 20. We simply calculate for a size of 20 if the frequency is 35, what should be the frequency when the size is 10? That is 35 divided by 20 and the product is multiplied by 10. Here it is 17.5. Thus we get a new table where the frequency of the unequal class changes and a histogram is constructed. Another way of representing data is by frequency polygons. A frequency polygon is a graph constructed by using lines to join the midpoints of each class interval. The heights of the points represent the frequencies for intervals. A frequency polygon can be created from a histogram or by calculating the midpoints of the class intervals from the frequency distribution table. Using the previous histogram, if we plot the midpoint of the top of the bars, the result is a frequency polygon. In fact, frequency polygons can also be created without using histograms. We find out the class mark for each interval, that is, the midpoint for each class, and against those we plot a graph which gives us the frequency polygon. Mathematically, class mark is obtained by adding the upper and lower limit for each interval and then dividing the result by 2. Thus, for the first class interval, it is 19.5 plus 29.5 whole divided by 2, which is equal to 24.5. We do this for each class mark as shown in the table, and then we plot a graph to obtain a frequency polygon. Do you think that the area of a histogram and the area of a frequency polygon will be the same when they are constructed from the same data? If so, why? Do you know what the areas signify? All these will be answered in our future lessons. I hope you have got a fair idea about the basics of how data is collected and represented. In the future lessons, we shall learn about how they can be analyzed. Till then, stay curious and stay informed. See you soon.